Chapter 10, we're going to be looking at the functional groups of alcohols, which are carbons with OHs attached to them. So when we look at functional groups this semester, just as we did last semester, we're going to start with talking about physical properties, then move into a little bit of naming, and then what we'll do is then we'll review any reactions that we know how to prepare that functional group. So we'll talk about how you make alcohols in this chapter, and we'll review the reactions you learned last semester. Hopefully you remember that from last semester. And then we go on to the reactions of alcohols as the last part. So we'll start with alcohols and first of all deal with their structure and their classification. So if you look at alcohols, it's an OH group attached to a carbon. The oxygen we know from last semester is sp3 hybridized. It has two lone pairs and it has a hydrogen. So what we're going to find is that the alcohol, the oxygen of the alcohol, can accept a proton. So it's going to be a Bronsted base, but it could also give up a proton and act as a Bronsted acid. And so alcohols have the ability to be both Bronsted acids and bases. Now, if we look at the ability to donate electron pairs to a proton, that also makes the oxygen a Lewis acid. So alcohols then themselves, because they're electron rich, we would classify those as nucleophiles. And that's going to be, we've already seen those reactions occur. We've taken alcohols, for instance, and reacted them with carbocations in solvolysis reactions. So we've already seen the OH group, particularly the O, act as a nucleophile. So that's a little bit about the structure. We also know that if you have an alcohol, that the intermolecular forces that it can undergo, it can certainly accept a hydrogen bond from another molecule, and it can donate a hydrogen bond to another molecule that has an oxygen, nitrogen, or fluorine attached to it. Now, in terms of the classifications of alcohols, we classify alcohols based on the same criteria that we use to classify alkyl halides. So in other words, we look at the carbon that the OH group is attached to, and if that carbon has one other carbon attached to it, it's primary. If it's got two carbons attached to it, it's secondary, and if there's three, it's tertiary. And this is going to be important because depending upon the type of carbon that's attached to an OH, we saw last semester that if we protonate the OH and make it an oxonium ion, whether this is primary, secondary, or tertiary is going to make a big difference in whether that OH, well, not the OH group, but the water molecule can leave to form a carbocation. So we've already seen that, those reactions, but now we'll just make the classification formal. Now, you can't have an OH group attached to a benzene ring, and when that happens, you have a phenol. And phenols have a little bit different acid properties than a regular alcohol, and we'll talk about those in a few minutes. But phenols we will actually talk about in a lot more detail later on when we talk about the aromatic ring. Phenols were initially first used as disinfectants in medicine. It was found that phenol itself, which people actually got from taking coal and heating it in the absence of air, so in other words not burning coal, but what we call destructive distillation of coal, they actually got aromatic compounds with OH groups, the phenol itself, and it was found that it actually acted as an antiseptic by killing germs on the surface of the skin. We don't use phenols anymore as disinfectants or as antiseptics simply because phenol is a little toxic to the skin. So all of the disinfectants that we use, some of them anyway, are actually derivatives where there are other groups attached to the benzene ring to keep them less toxic. But we'll talk about the acid-base characteristics of phenol here in a minute or two. Now, in terms of naming alcohols, and I'm not really going to get into the naming of phenols right at the moment, we'll save that for chapter 15, I believe, when we talk about aromatic rings. But when you name alcohols, it turns out that the naming system is very similar to that we've used for alkanes, alkenes, and alkynes last semester. The difference is that the OH group now takes priority. So an OH group would take priority over a carbon-carbon double bond or over a carbon-carbon triple bond. And what you have to remember is that the OH group, because there's an oxygen, it would have a higher priority in the Con-Ingle pre-log sequence rules. Remember, those are the rules that we used for assigning groups priority number 1 and number 4. The OH groups basically have priority over the carbon-carbon double or triple bonds. So we'll look at some examples. If you have an OH in your molecule, it turns out that will actually have precedence both in the numbering scheme as well as in the naming. So what we do is we locate the longest continuous carbon chain that contains the carbon attached to the OH. And then we number from the end that's closest to the carbon with the OH group attached to it. As I said, the OH takes precedence. And then we'll name and number and alphabetize the substituents. And on this slide I actually have the old rules for naming alcohols. And in your textbook they talk about the new changes that have been made to the IUPAC names for naming alcohols. And I'm going to actually go over both of them, and to be honest, I'd probably accept both names, the older system as well as the newer one. But let's take, for example, this molecule. So if I want to write the IUPAC name of this, what I would do is I would find the longest continuous carbon chain in the molecule that contains the carbon attached to the OH. And in this case, this is a 5-carbon chain. So it turns out this is going to be a pentane. It's actually going to be a pentanol ring. So we number at the end closest to the OH, which in this case this would be carbon 1, 2, 3, 4, and 5. If I had a tie in the numbering scheme, I would then look for the first alphabetized substituent that's closer to that end. So I've got 1, 2, 3, 4, 5. So at carbon 3 I have a methyl group, and at carbon 1 I have a chloro. So in writing this name I would do exactly what I did last semester. This is going to become a 1-chloro, 3-methyl, and then it's going to be a pentanol is going to be the name. So we'll have the parent name with the AN sort of suffix, and then add OL to it. Now in the old system I would have called this 1-chloro, 3-methyl, 1-pentanol, where the 1 tells you that the OH group is attached to carbon 1 in the 5-carbon chain. Apparently this is the old IUPAC system. The new IUPAC system, the name of this would be 1-chloro, 3-methyl, and then we would have pentane, and then we would have the 1 and the OL. So in the new IUPAC system, they simply write out the longest chain parent name, add the number of the OH group, and then add the OL like this. and honestly, I have no idea how long they've changed this rule for, but this is what's in the textbook. I'll accept either answer because I think not everybody's made the switch to the new system. So the idea here is that you have to tell me what the longest chain is, and then you have to tell me where the OH group is. Now, if you had more than one OH in your molecule, then you would use the di, a di prefix to that. So let's take something fairly simple. This is a molecule. Its common name is called ethylene glycol. Glycols have OH groups that are attached to carbons next to each other. Ethylene glycol is the major component of your environmentally not so friendly antifreeze. But this ethylene glycol's IUPAC name would, in the older system, have been 1,2-ethane diol. Would have been its name, simply because that tells you you've got a 2-carbon chain, and the OH groups are attached to carbon 1 and carbon 2. And it's important, again, to have 2 numbers whenever you use the di as a prefix. I believe in the new system this would be called ethane 1,2 diol. So either system, again, would work. And so if you have more than one OH group in a non-cyclic alkane, then you can go ahead and write it either way. This first one is actually my preference. Okay, so let's take a look at another molecule. Let's throw a double bond in here. So how do we name molecules that have like a double or a triple bond and an OH in them? Well, we've already said that the OH takes precedence, and what I mean by that is that we have to number from the end closest to the OH group, as well as then give that number as the last one in the name. So in this case, I would number the longest continuous carbon chain that has the OH group in it like this. That would be a 6-carbon chain, so this is going to be a hexane. In this case, I've only got one substituent, and that's attached to carbon 2. Well, actually, I have no substituents. The OH group is attached to carbon 2. So there's both a new and an old way of naming this. The old system would have been to name this 4-hexene. Now, I'm telling you that there's a double bond in the 6-carbon chain, and that's at carbon 4. And then you would have 2-ol. Would be the old. This would be the old system of naming this alcohol that has an alkene in the parent chain. In the new system, they actually just changed these around a little bit, so this would be called hex 4-ene 2-ol. And so in your textbook, that's what they talk about as the new system. So again, either way, the key thing is that because the OH group has precedence or has priority, it comes as the last number next to the OL. So if I'm reading this name, what I'm seeing is a 6-carbon chain with a double bond at carbon 4, or between carbons 4 and 5, and an OH group at carbon 2. Okay. If I would have had this molecule, and I would have given you a particular cis-trans isomer of this, let's say I could have written this structure. In the first structure, I didn't show a stereochemistry, But now if I do, you would have to put the cis or trans or E or Z in front of the name in order to get the proper name of this. And so in this case, we would have this one being, this is trans, and in the older system this would have been a trans 4-hexene to all, or in the new system it would be trans hex 4-ene to all. Okay. So we're following similar rules that we learned last semester for alkanes, alkenes, and alkynes. For cyclic alcohols, they take precedence, and so wherever there's an OH group attached, that OH group automatically then gets the number 1 carbon position in the numbering scheme. And then you would go clockwise or counterclockwise in order to find the first substituent. There's no total sum of numbers here, and I'll repeat that. There's not a total sum of numbers here. We would simply start at carbon 1, and then in this case we would number carbon 2, 3, 4, and 5 because we've encountered our first substituent at carbon 2. If you had a tie, then you would use alphabetization to break the tie, but only if there was a tie in terms of that finding that first substituent after starting at the OH. So in this case, this one would be called 5-bromo 2-chloro, and then cyclohex and all. You don't have to put the number 1 in the cyclohexanol name because it's understood that the OH group is automatically at carbon 1. Okay? And so you would do that. If you had 2 OHs on a cyclopentane ring, then you would have to start at one or the other, and the rules would probably be that you would look to try and find the first substituent after you did the numbering scheme. But let's just take it and make it quite simple. In this case, we have this would be called cyclopentane diol, and it would be 1,3 cyclopentane diol. And there wouldn't be a hyphen here. It would just be and you might say, why is it cyclopentane instead of cyclopentan, cyclopentan? Because it's easier to say if it's cyclopentane. So again, these are just sort of the basic naming rules for these. I'm sure that if you were in the new system, this would be called cyclopentane with no E, and then 1,3 diol. But again, either system is fine. So, I mean, naming isn't going to be that important of an issue as we go through the semester, because what we're really interested in are the reactions and how to synthesize these different functional groups. Okay, but those are the basic naming schemes, and you can look in the book to get a lot more of the technical details on that. And in your online quiz, the pre-lecture online quiz, you'll have some naming that you will type in the names into the quiz for. And for those of you that are new, when you type in the names, I actually go through and grade those by hand. So unless you have my name exactly perfect with all the spaces and everything else in exactly the same space, the computer will mark it wrong, but that's okay. I go back through and I grade it by hand. Okay, so that's naming. I guess I should probably add one other thing because it's in your book about the naming, and that is that they did something like, they actually did something like this where they had an OH group attached as part of a substituent. When OH groups are part of a complex substituent, we actually name those as a hydroxyl, as a hydroxy group. So for instance, in this molecule, I would start numbering here, and that would be carbon number 2. Now what do you call this group? Well, I'm going to treat the OH group as if it was a hydroxy group. Okay, and then we would name this complex substituent exactly the same as we named it last semester using our IUPAC rules. So in other words, there's a 2-carbon chain here, and we automatically have to start numbering at the attachment point. So that's carbon 1, carbon 2, so this is an ethyl group. And the actual name of this molecule would be 2, and then in parentheses the complex substituent name, which would be 2-hydroxy ethyl, and then cyclopentanol. That would be the IUPAC name of this, including the name of the complex substituent. So I guess my point is that for the complex substituents, you actually use the hydroxy as the OH. You treat OH as a substituent called a hydroxy group, and then name it the same way that you would name any other substituent, like a chloro or a bromo. You also would then alphabetize it according to the H. Okay? So that's the naming of alcohols, both cyclic and straight chained. Now let's just for a minute, because there's a section in your book about sort of just the commercially available alcohols, and it turns out that alcohols are important solvents, also fuels, and some of the important commercially available ones are the 1-carbon alcohol, which is called methanol. Methanol is also called wood alcohol because you can actually take wood and destructively distill it to make ethanol or to make methanol. If you take wood and you heat it in the absence of air, so in other words you're not burning the wood but you're distilling it, the distillate that you collect off the wood will be methanol, and so that's called wood alcohol. Methanol, where do we use methanol nowadays? We've used it in the lab as a solvent. It's in most of your window wiper fluids, the blue solution you put in your car. Methanol will reduce the freezing point of water, so it makes a good de-icer and cleaner for your windshield. It's also has been used in the past as a fuel in things like Indianapolis race cars, in the Indy cars. Problem with methanol is when it burns, it has a nearly invisible flame, and so it's a very difficult thing to burn practically because you may or may not see the flame, and that was a problem within the race cars. It's poisonous. If you drink wood alcohol, the best case scenario is you'll go blind. Worst case scenario is you'll die. So methanol is a poison. Ethanol, CH3CH2OH, is called grain alcohol. You can make it by the fermentation of sucrose and other organic materials. Nowadays there's the big push to take cellulosic material and try and convert the cellulose into ethanol. That's where you're hopefully eventually one of these days going to be able to take your lawn clippings and make ethanol out of it so that you can use in your car. And I don't see that day coming in the near future, but that's what people are trying to do, and that's what they do in terms of trying to take that's what we're using a lot of corn for now in terms of making ethanol to add to gasoline as a blend. So ethanol is used as a solvent If it is fermented, it can be used as an adult beverage. The There is an industrial preparation of ethanol where you can actually make ethanol from an epoxide, and we talked about epoxides last semester. That will give you an industrial grade alcohol. Alcohol is very difficult to purify. If you're doing fermentation to make alcohol, and those of you that were in lab last semester, we did the fermentation of the yeast in the ethanoacetoacetate experiment, and we actually made a solution that had a lot of ethanol in it. If you do fermentation, it's difficult to get absolute ethanol, which would be 100%, because when you distill ethanol in the presence of water, what you end up getting is a 95:5 ratio of ethanol to water, and that distillate always comes out as a 95:5 ratio. That's actually what's called an azeotrope. And so you have to do special things in order to get the alcohol to 100%. If you're into alcohol, then the percentage and the proof is simply twice the percentage. So if you have a beverage that has 200 proof alcohol, that means it's 100% or it's absolute. One of the issues with making 200 proof alcohol is simply the fact that it's difficult to remove the water, and so some of the processes that are done to remove the water can leave impurities in the ethanol that can cause bad reactions if you are consuming 200 proof alcohol. 190 proof would be the 95:5 azeotrope that you would normally get, and then of course it can be diluted from there. The alcohol that we use in the lab is not that can be consumed. It's actually what's called denatured alcohol. Alcohol has a historical, it's a historical thing particularly in American history, because it's been taxed all along. I believe one of the early wars within the United States was over the taxing of alcohol. And of course we still have issues of moonshiners and things like that. At least that's what I see when I look at TV sometimes. Denatured alcohol is what we use in the lab, and that's alcohol that's had something added to it to make it undrinkable. And the reason that we use the denatured alcohol in the lab is not because we're worried about students consuming it, because you'd have to be an idiot to do that if it has toxic things like benzene and other things added to it. Just a word of warning if you ever were dumb enough to think about doing that. But the reason that we use denatured alcohol is if it's undrinkable, then it's not subject to tax. If it's drinkable alcohol, then it is subject to tax, and there's a whole just government paperwork that you have to do to have absolute ethanol. So what we find in the stockroom is actually denatured. That's what we use in the lab. Ethanol, of course, talk about it, using it as a fuel, blending it with gasoline, potentially, I suppose, using it as its own fuel in cars, most likely blended with gasoline of some type. And the easy way to make ethanol is simply to ferment sugar. The more difficult is to ferment other cellulosic materials, other materials made of cellulose. And so right now we do have ethanol blended alcohols, or ethanol blended gasolines, but they're not progressing nearly as quickly as people had thought. Other important alcohols, we have isopropyl alcohol, which is rubbing alcohol. That's simply an isopropyl group attached to an OH. That's what you can buy at the drugstore in different percentages, 50-50, 70-30. It's used primarily just for cleaning skin and some level of disinfectant. So those are the commercially available alcohols that we sort of encounter in the lab and in life. The last sort of the last things that we'll talk about with alcohols, at least in this introductory lecture, is the idea of the acidity and basicity to some extent of alcohols, but we'll deal with acidity first. So if you have an alcohol, the alcohol has the oxygen with lone pairs, which makes it have the ability to accept a proton. It also has a proton, so it can donate one. So, of course, if you donate a proton, let's say we write an equilibrium where we take the alcohol, react it with water, then we can have this acid equilibrium where the alcohol will donate a proton to water, or we can have the alcohol accept a proton from water to make an oxonium ion and a hydroxide. So the alcohol can act either as a Bronsted acid or a Bronsted base. Now, let's look at it. We'll look at it in terms of being a Bronsted acid first. Well, if you looked at the pKa of the alcohol, it's anywhere from 16 to 18, which really classifies it as an extremely weak acid. If you put alcohol in water, you will get very little dissociation to form the alkoxide and hydronium ion. Now, one of the things that we have to talk about, and I'm just going to briefly introduce it here, is how can you have, your pKa scale in water as a solvent goes up to 16. And the pH scale, remember, that sets the pH scale from, the pKa of water is 16 in an organic solvent, as opposed to in pure water. In pure water, we know that the pKa of water is 14. But this pKa, this is actually in an organic solvent. So if you looked at that to begin with and say, wait, you don't remember your general chemistry, pKa of water is 14. It is in pure water, but when you go to an organic solvent, it changes a little bit. And so it turns out that alcohols are weaker acids, or at best equal acids to water. And so what that means is that this equilibrium, when I write this, there's very, very little alkoxide formed, or there's very little oxonium ion that's formed. So if you dissolved an alcohol in water and measured the pH, which actually isn't as easy as it seems, you would end up with a pH that's approximately neutral, because you'd have very little hydronium and very little hydroxide formed. If we look at the periodic table, remember that when last semester we looked at the acid and base trends for the periodic table. So remember that if you have a CH, an NH, an OH, and HF, that as we went across the periodic table from left to right, we formed the stronger acid. So HF was a stronger acid than a CH. And of course, when we went down the periodic table, acid strength got stronger, so that HI was a stronger acid than HF. Well, if we know the trend for acid strength, we can then say, well, what's the relationship between C minus, N minus, O minus, and F minus as bases? Well, if you said that going from right to left, we have stronger bases, then you're correct. So C minus is the strongest base in that series, and F minus is the weakest base. So we want to keep this in mind, because if I want to deprotonate an alcohol to make an alkoxide, I'm going to have to use a base that's stronger than O minus in order to get complete dissociation. And so when I say that we have to use C minus or N minus, or actually H minus, because if we looked at this, H minus would actually have about the same basicity as C minus. Those are the three bases that we can use to completely 100% dissociate or deprotonate an OH group. So when I want to make alkoxides, okay, going back here, we have talked and will talk in more detail about protonating OH groups to form oxonium ions. If you remember from last semester, we did that when we did dehydration reactions of alcohols. And so we added either sulfuric or phosphoric acid, or I substituted an OH group with a Cl or a Br by adding HCl or HBr. So the second step, I'm going to accomplish this second step of protonating the OH simply by adding H+, and that H+ is either going to come from sulfuric, phosphoric, or it would come from HCl or HBr. But remember, these two lead to dehydration reactions, and these lead to substitution. So we'll talk about that when we talk about reactions of alcohols, which actually is in the chapter 11, the next chapter. Now what I want to do is I want to talk about how do we deprotonate alcohols to form alkoxides. And so in order to do that, what we would need to do is to simply react the alcohol with a base that's strong enough to deprotonate the alcohol to make the alkoxide. And you might say, well, why do I want to make alkoxides? Well, you could answer that if you remember from last semester that we could use alkoxides as bases in E2 eliminations. Small alkoxides we could also use as nucleophiles to do SN1, primarily SN2 reactions. So the bases that we would use then to deprotonate the alcohol would be our H-, our C-, and N-, all of the bases that are stronger than O-. But before I talk about the deprotonation, which I will in a moment, there's another way to make alkoxides, and that's to react them with either sodium or potassium metal. And this is a similar reaction that you learned in general chemistry. In general chemistry, you may have talked about, well, you did talk about the reaction of an alkali metal with water. Something like sodium or potassium or cesium or lithium with water. This is a redox reaction, and it's also called a hydrogen displacement reaction, if you remember that from general chemistry. Basically, what happens is that if you take sodium and react it with water, you will get sodium hydroxide and hydrogen gas. Whoever you had for general chemistry may have showed you a video on it. It's usually a fairly spectacular video because it usually involves hydrogen gas then igniting and catching on fire. I don't know that anybody is brave enough to actually do it in class, but they may have dropped a little piece of sodium metal into the water and shown you that reaction live. If you don't remember what that looks like, Google it or go to YouTube and type sodium reacting with water, and I'm sure you'll find all sorts of demonstrations that should never be accomplished at home. But the point here is that we make sodium hydroxide and we make hydrogen gas. So the redox part of this is sodium going from an oxidation number of 0 to +1, and hydrogen going from an oxidation of +1 to 0. But we never worried too much about the sodium hydroxide. The hydrogen was always the important product there. But now what I'm going to say is this. Water is HOH, alcohol is ROH. So I can do the same reaction by taking an alcohol, adding sodium metal to it. I'll still make the hydrogen gas, but in this case I'll make the alkoxide. And so one way to make alkoxides is to do this oxidation reduction reaction using an alkali metal like sodium or potassium, or in my lab we actually many years ago we did this with cesium, which is a little scary. But you can actually do this reaction fairly straightforwardly. As a matter of fact, one of the early preparations, and still probably the best preparation of potassium tertiary-butoxide, if you remember, potassium tertiary-butoxide is what we used to do E2 reactions because it was our sterically hindered strong base. So that if we reacted our tertiary butyl alcohol with potassium metal, we would make potassium tertiary-butoxide, and of course we would make hydrogen gas over here as the other product. So that's typically how we make potassium tertiary-butoxide. So that's the first method to make an alkoxide, or to net deprotonate the alcohol. And of course we know what to do with alkoxides. We do E2 eliminations, or we could potentially do SN2 if we had very small sterically non-hindered alkoxides. So if we're going to do the deprotonation reaction, as I've already kind of laid out earlier, what we need to do is we need to deprotonate the alcohol 100%. Well, hydroxide isn't strong enough to completely deprotonate an alcohol. The pKa of water and the pKa of the alcohol are very similar, and so therefore at best I get an equilibrium. If I want 100% completely deprotonate an alcohol, I'm going to use an N- or I'm going to use a C-, because then I will get complete deprotonation. And again, the reason for that is because C- and N- are stronger bases than an O- species from the periodic table. Well, our N- base that I might use is our amide. We used amide to do E2 eliminations. It was our small base. And we also did we also used NH2- to deprotonate a terminal alkyne. Remember, a triple bond with hydrogen at the end of it. We can also deprotonate alcohols with C-. The only C- that we know right now is an alkynyl anion. And so if you made an alkynyl anion, you could use it to deprotonate the alcohol. Now later on in a couple of lectures we'll talk more about how to make carbanions from things like with methyl groups and ethyl groups, very simple carbanions. But right now the only one that we know how to make is an alkynyl carbanion, or an alkynyl anion, and the way that we made that was to react that terminal alkyne with our NH2- to make the alkynyl anion. So we can completely deprotonate an alcohol using either one of these two bases. So if you want to make an alkoxide, you can use sodium, or you can use amide, or you can use a C- species to completely deprotonate the OH. You can also use an H-, which is called the hydride ion. Now, where did we see hydride ions last semester? We saw them in what? Sodium borohydride, which was a reagent that we used in some of our alkene addition reactions. But actually in this case, hydride, the hydride I would either use is potassium hydride or sodium hydride. These are pretty wicked reagents. Sometimes you could use calcium hydride, but usually you'd use potassium or sodium hydride to deprotonate the alcohol. And there are advantages and disadvantages of those as well. But we can use a N-, H-, or C- to completely deprotonate an alcohol. So if I want to make an alkoxide, I can either use the redox reaction of sodium or potassium metal, or I could use the stronger base than an alcohol, and that would allow me to make alkoxides. And there's the sodium hydride reaction. Okay. Now, phenols have a slightly different acid-base property than alcohols. A phenol turns out to actually be more acidic than your run-of-the-mill alcohol. And so you can actually deprotonate a phenol using hydroxide. If something's a stronger acid, it means that you can use a weaker base in order to deprotonate it. And so phenols can be deprotonated by hydroxide very easily and in 100% yield. So the reason for this, and this will be the second to last topic here, is that if you took an alcohol and deprotonated it, there are no resonance structures possible for an alkoxide ion. There's no way to move this pair of electrons and form any kind of resonance structure. But if you take a phenol and deprotonate it, you end up forming what's called a phenoxide ion. And that phenoxide ion has 3 more resonance structures that you can draw. You could take this pair of electrons, move here, and then take this pair of electrons and have the minus charge on that carbon. And then move this pair of electrons here and move that pair of electrons out to form this C minus. And have this pair of electrons move here to form that C minus. So the more resonance structures you can draw for a molecule, you can finish the sentence, the more stable it is. And the more stable the conjugate base is, what happens to the equilibrium? The equilibrium gets pushed towards the more stable species. You end up with more protons being formed, and therefore this is a way to push the acid-base equilibrium to the right without using Le Chatelier's principle. The more stable the conjugate base, the stronger the acid. We talked about that numerous times last semester. So phenol, because it forms a more stable conjugate base because of all these resonance structures, is more acidic and therefore can be deprotonated by something as simple as hydroxide. Did we see this last semester? Well, not in lecture, but we did see it in lab, if I remember correctly. Or we could have seen it in lab. It turns out that in the lab we can actually extract phenols using sodium hydroxide. And the idea here is that if you had a phenol, and last semester the phenol that we used in our lab experiments was this phenol, acetaminophen. So we could have actually extracted acetaminophen into the aqueous layer, and we didn't do that last semester, but we could have if we would have treated the acetaminophen with hydroxide. And so what would have happened is the hydroxide would have deprotonated the OH to form an ionic substance that then would have dissolved in water. And if you wanted to separate a phenol from, let's say, something like cyclohexanol, if you treated these two with hydroxide, you would only deprotonate the acetaminophen. It would go into the aqueous layer, whereas the cyclohexanol would stay in the organic layer. And so you could very easily separate acetaminophen from an alcohol simply by extracting it with hydroxide. Okay, so this is the initial part. These are the initial parts of alcohols for this coming lecture. So the important things to remember are naming of the alcohols, how to name them with the IUPAC system, and then the acid-base characteristics. How do we deprotonate alcohols to make alkoxides, either by using a C minus, H minus, or N minus, or using the redox reaction of sodium, potassium, any alkali metal will make the alkoxide and hydrogen gas. Okay. So after you've watched this video, this is over in a minute, actually a few seconds, then you will go ahead and look at the sections from the textbook, and then there are homework problems, or there are online quiz problems that you'll do on Blackboard. They're due before 8 or 9 o'clock of the next period, depending on what section you're in. And also, if something didn't make sense during this, bring it to class, and that's the first thing that we will talk about is, are there any questions, and I can go back over something that didn't make sense.